for the very warm welcome and hospitality that they are offering us. So it's my second time in Norway, first time here in Stavanger. I think the city is very nice. We just had a look yesterday, but it's very welcoming. And I plan to come and visit a little bit more, maybe in the next future. So a couple of words to introduce my university. We are in Padova, and Padova is in Italy. And well, I think this is clear from Gianfranco's presentation. What might not be clear is where in Italy Padova is located. Where we are here, and Venice is here. So it's a very nice location if you plan to go and visit Venice. But also Padova is pretty nice, so I really welcome you to come and visit our city and our university. As Gianfranco was mentioning, this year, we celebrate 800 years of history. So it was founded in 1222. And is one of the world-class universities and the first one in Italy for research and teaching quality, according to a national evaluation board that evaluated all universities in Italy. And according to different ranking organizations, we are in the top 250 universities in the world. That is pretty good. And we are a research-intensive university, so we do not only teach, but we do research as our main, let's say, mission. And it's a generalist university, so we have all possible disciplines and faculties and departments and everything. So interdisciplinarity and multidisciplinarity is one of the key aspects of our university. 60,000 students, more or less. We do not count each of them day by day, but the number is more or less that. We have an increasing number of international students. We kind of double the number of international students every year in the last period because we are pushing a lot towards international students. We started a number of master degrees in English. So this attracts a lot of students from foreign countries, but of course also European students are very welcome. By the way, for us, European students are not international students, are just European students, like local ones. So international, we mean outside Europe. And we are around 2,300 faculty members and as many technical and administrative persons that work on 32 departments, 8 schools, and so on. So it's a big university, one of the biggest in Italy. This is the let's say, old lecture hall, one of our, I would say, most beautiful rooms in the old university. University of Padova, as many universities in Italy, doesn't have a campus. It's a distributed university. So in the very downtown, we have the old building with these rooms that we just use for very special events. For example, when you have to present university to another university, right? You show these kind of rooms, but typically we do not teach in these kind of rooms, unfortunately. And our motto is Universal Universis Patavina Libertas, is in Latin. It means that the freedom of University of Padova is complete and for everyone. And the reason why we have this motto is that University of Padova was built by students and professors that were looking for the freedom of study back in 1222, where, you know, science was not so open to all possible disciplines and to everyone. Well, people escaped University of Bologna, that was the oldest one at that time, and founded University of Padova just to have the freedom of teaching and learning what they want to teach and learn. And we are very proud to have graduated the first woman in the world back in 1678, Elena Lucrezia Cornaro Piscopia. And starting from October this year, we also have our first woman rector of the university. So, you know, thanks to God, things are evolving also in these terms. So Padova is pretty nice. So you are really invited to come and visit. We also have our very small lake as here in the city center. It's not really a lake actually, but still. And it's a very, you know, it's not a big city. I think it's very comfy and cozy also as an experience. Well, talking about my research group is called SIGNET. This is just a picture of some of us. We are about 25, 28 people, depending on the year. And if you want to know what we do, you can visit our website. It's signet.dei.unipd.it. And there you find all the different activities we do. Since we are a lot of people, we do a lot of things. So we are very active in mobile networking, Internet of Things, smart cities, energy, harvesting systems, underwater communications, AI. So we do a lot of things, right? We have many people involved in many different research projects, and also some more exotic things like microfluidic networking. That is something that I play with in my spare time, which means that I don't play at all because I don't have much spare time, unfortunately. All right, that's all for the introduction of my research group. And now let's go to the content of this talk. So this is a brief outline. I will start with some motivations that I try to keep as short as possible because it's the standard things that you say to motivate your work. And then I provide some examples of the activities that we do in the big domain of machine learning, protocol optimization, and multimedia service support, and so on. I realized that I prepared way too many slides for the time that I have. So I think we have to select the topic that we like the most. And I propose some options for you. Then I leave the floor to my colleague, Federico, who is here, who will go a little bit deeper into the details of one specific activity that we are carrying on also together with Gianfranco regarding network slicing. And finally, I'll try to conclude with some final remarks. So quickly, motivations. So we know that all smart things, like smart cities, is not just one thing, right? It's a set of many different things. So in smart cities, we have smart governance, citizens, mobility, utilities, and so on. So a number of services that need to cooperate and to improve in terms of efficiency, sustainability, and also, let's say, easiness of use, right? It should come almost natural to the user. Saying, well, similar things to industry, the smartness in industry can be, let's say, summarized in these characteristics of the production process. It should be innovative. It should allow customization while maintaining mass production. So the industry process should become very modular and flexible in order to allow personalization without increasing too much the costs of the manufacturing. Should provide self-maintenance, predictive maintenance, that is one of the hot topics today in Industry 4.0, and should provide support for human operators. So the human component is very central in Industry 4.0, despite what people might think of. Well, many of these services build upon data that have to be generated by suitable sensors and transmitted to a center where data can be accessed and processed in order to find the information that can be exploited, right? So these are the typical 5 steps that we need to go through in order to realize a smart service. Well, in this talk, I will focus primarily on these 2 points here. So the generation of data and the transmission of data. Why? Because they are kind of fundamental in my point of view in order to realize a smart service. The communication systems that we have today have been designed for services that were required 5 years back, let's say, right? So we have communication systems that support maybe massive data transfer, very high throughput. You can watch a movie on your mobile phone in the train, so it's good. But new services have different requirements, right? So they require interactivity. So they require very small delays. That's the reason why Gianfranco was mentioning the edge computing. We try to move the computing towards the user to reduce the delay. They require guarantees in terms of delays. They require adaptable resources. So one thing that I remember when I was participating to one of the first meetings discussing 5G services. So at that time, I remember I was sitting and one guy showed a slide with the requirements for these new 5G systems. And one of the requirements was infinite capacity. I said, well, that's a kind of challenging requirement, right? So it's not that easy to realize infinite capacity. But the idea there was that infinite capacity is just enough to satisfy the user requirements, right? So if the user gets what he or she needs, for his or her perspective, the capacity is infinite. And this is the purpose. So you should provide resources where needed, when needed. So we need something very dynamic and adjustable to the requirements of the applications. So trying to summarize this short introduction, the motivation slides, we have new markets and new applications that set very specific and often stringent quality of service requirements to the communication plane. And in order to meet these requirements, we need to develop new methodologies. We need to have a transmission service that must be efficient, so use resources in a clever manner, adaptable, so need to reallocate the resources as required, and customizable. So different services might need different type of communication structure, communication service. How to realize these goals? Well, the first approach should be to take the technologies that we already have and try to optimize them. So based on our experience, modern technologies, many of them, are very, let's say, I would say customizable, even though this is not the right term, but they provide a number of tuning knobs. And if you tune the different knobs in the proper manner, then you can have very different type of service that you provide to your customers. So the first thing is try to properly configure the technologies that you can get off the shelf. However, in some cases, this is not enough, and you have to come up with new protocols and new solutions in order to provide the services that are required. So our approach is to work on these two, let's say, taking these two paradigms, first trying to optimize what we have, understand how it works, and try to set the parameters in order to meet the requirements. And the second approach is to develop something new based on a deep analysis of the requirements of the applications. Good. Then, in the next bunch of slides, I will just give you a very high overview of some of the approaches that we following this paradigm, right? And I call these approaches S-Cube, that stands for Smart Sensing and Sending. I hope you like this name. I came up with it yesterday night, so it's brand new just for you guys. All right, so this S-Cube approach will be explained using some examples that I've taken from the work that have been done in the last years by my group. One regarding the modeling, tuning, and the use of LoRa, that is a technology for Internet of Things. I will explain what it is. And then another approach consists in the analysis of delay constraint transport protocols. So the design of new transport protocol end-to-end that can meet some hard delay requirements. Before starting, a brief explanation of the idea behind this approach. So I would say that this line of research started a few years back, thanks to a project funded by Intel. Intel funded a few universities in the US and our university, the only one outside US actually, to develop very low energy radio devices. And all the other universities were working on the electronic parts of these devices, on the hardware. We were the only one working on the software. And the reason was that, well, you can have a very power efficient hardware, but you can waste the capacity of this hardware if you design the protocols, the communication protocols, in an ill manner. So the idea there was to say, well, do not only try to optimize the hardware, you have also to optimize the software, so the communication protocols, being aware of the capabilities of your hardware. And following this very basic idea, we came up with some proposals that then we developed over time also in other scenarios. One of which was to provide mathematical and numerical models for the system components, so a sort of digital twins. We usually try to model our system. We try to realize the model in simulations, or in some cases, if the model is not too complex, or also to come up with a mathematical model of the system. And then using this simulated or mathematical model, we can try different combinations of the parameters in different scenarios and see how the system is expected to work. So we realize what might be seen as a sort of digital twins of the system. And we play with this digital twin to understand what is the proper setting of the parameters of the system for the different application scenarios. And another approach that we successfully actually attempted was to model, well, in certain scenarios, right? In many cases, you have an application that generates data, and those data have to be delivered to the destination. But in many cases, the application is kind of flexible. So it can decide the quality of the data and maybe the frequency at which data are generated and so on. And there is a trade-off typically between quality and bitrate. So the application can decide to decrease the quality in order to decrease the bitrate of the stream of data that needs to be transmitted. What is difficult to capture is this quality rate characteristics, because this depends on the application. Consider, for example, a video, right? In video streaming, it's common experience that you can decide the quality of the video to download from YouTube, for example, and if you decrease the quality, the stream is lighter. So if your connection is so and so, you can download the video with a lower quality. What is not that clear is that the ratio between the quality that you perceive and the bitrate depends on the video. So if you have very dynamic video, in order to squeeze it in terms of bitrate, you have to decrease a lot the quality, the perceived quality. If the video is very boring, like this video that we are recording now, with just a standing person talking, standing almost still, then it is very easy to compress the video without losing quality. And this is something that is not easy to capture beforehand, right? You cannot have just one curve, rate distortion. It depends on the content of the video that you are looking at. So our idea here was to use machine learning to estimate the rate distortion curve for that specific content and optimize the protocol, the transmission protocol for that specific content. So you don't have a protocol for video and protocol for audio. You have a protocol for that video and a protocol for that audio. That is something new. And actually it works pretty well. So the idea eventually is to generally optimize the sensing, so the production of the data, and the sending, the transmission of the data. You have to consider these two aspects together in order to really obtain the best from your system. All right, examples. I prepared 3 blocks of examples for this type of approach. One regards the energy efficient environmental monitoring, so how to collect data from the environment in an energy efficient manner. The second one regards LoRa, the protocol that I mentioned, used for mainly, or better, proposed for the Internet of Things domain, but can be also used in other contexts like the control of drones or in industrial settings. And the third one is the design of delay constrained transport protocols. That is something very recent that some solutions that we came up with very recently. So please guys, choose. You can vote for, well, there's a fourth option that is to jump directly to the conclusions, but this is not actually available. So you can choose first, second, or third example. Choice is yours. So raise your hands for the first one. 2 persons, just one person here in the room. Second option. All right.
I don't know why we have so
45. All right.
so it's like
All right. So we need really to choose. See, okay. Oh, second one. Raise your hands. Okay, let's go for the second one. Oh, that's not the second one. Why doesn't it work? All right, here it is. So LoRa, a couple of words about LoRa. I will skip some slides to save time. So how many of you guys here in the room are familiar with LoRa? So and so. All right, so very quickly, LoRa is a new technology, relatively new technology, let's say it has something like 7 or 8 years now, that is based on modulation based on what is called chirp spread spectrum. Is a type of modulation that was patented by Semtech, a French company, works on the 800 megahertz frequency band and provides up to 6 different transmission speeds. The transmission speed is determined by a parameter that is called spreading factor. So the larger the spreading factor, the longer the time on air of the packet, which means that the lower the transmission rate, right? So why should you lower the transmission rate? Because the lower the transmission rate, the longer the distance. So you have this trade-off. You can transmit with a relatively high speed over short distances, or you can reduce the speed and reach longer distances. LoRaWAN refers to the protocol stack, right? LoRa is just the modulation, LoRaWAN is the system. And the specifications are open, and they define the system as a star of stars, as they say. So we have the end devices that might be, distributed over a certain area. They broadcast their signal using the LoRa modulation. The signals are captured by some other devices that are called gateways that are much more powerful than the end devices. The gateways can decode multiple transmissions simultaneously, and they are typically connected to the internet using some standard internet technology. So all packets that are intercepted by the gateways are forwarded to a certain server that is called LoRa network server. And the network server is the brain of the system. The network server decides which packet. So first of all, it discards duplicate packets. You say when one device is in the coverage range of 2 gateways or more gateways, all of them will receive the packet and will forward the same packet to the LoRa network server. So the network server just discards duplicate packets. It picks one gateway to use for the return packet. If it has to reply to the transmission of the end device, it decides the setting of the different parameters in the system. So that's the brain of our system. Apart from that, the topology is very simple. You just deploy your end device, you switch it on, and it starts transmitting. And if you have a gateway in the coverage range, then you are connected to the LoRa network. So in this slide, you see the bit rates that you can get with the different spreading factors. So the larger the spreading factor, the lower the bit rate, but the longer the distance that you can reach. So these type of systems have been designed to provide relatively low bit rates. You can see from hundreds of bits per second to few kilobits per second, but over wide distances, large distances, 2 kilometers up to 14 kilometers in rural areas. And well, there are a few, I will skip some details, but something important here is that the medium access control, so the way in which the nodes transmit on the channel, is very basic in LoRa. So whenever a node has something to transmit, it just transmits the packet. But in order to reduce the interference in that channel, they have to respect what is called a duty cycle, which means that they can occupy the channel only for 1% of the time. So if they transmit for 1 second, they have to keep silence for 99 seconds, all right? So this is a very strict constraint. And the purpose is just to reduce the congestion on that frequencies. Now, in LoRa, the devices can be of different classes. The most common one is class A, that is used for battery-powered devices. So in that case, the device, the end device, ED, sleeps most of the time. Whenever it needs to transmit, it wakes up and transmits the packet. It chooses a certain uplink channel among those available, a certain spreading factor. It transmits this packet. The packet is received by the gateway, forwarded to the network server, and then the end device can wait for a reply in 2 receive windows immediately after the transmission. So it waits for 1 second, and then it opens this first receive window on the same channel and spreading factor used for the uplink transmission. If it doesn't receive anything here, it goes back to sleep for a few seconds, then open a second receive window a few seconds later. But This time it opens the reception window on the downlink channel. It's a dedicated channel just for downlink, so from transmission from the gateway to the device, and using the spreading factor 12, so the lowest available bitrate. Why is this important? Well, because these choices, so the fact that the first received window is open on the same channel used for the uplink transmission, the fact that we use the same spreading factor used for the uplink transmission, the fact that the second received window is open on the dedicated channel, and so on, all these factors do have an impact on the performance of the system. And what we did was to play with these factors and see what is the best configuration that we can obtain in different conditions. So let me skip a few slides. So we analyzed the system in two ways. First, we developed a synthetic version of the system using a network simulator that is called NS3. Maybe you know it. So we developed a very sophisticated model of the technology in this simulator that is, by the way, a pretty complex simulator, so it kind of realistic simulator. And we use this simulator to analyze the performance of the system with different parameter setting. We changed also some parameters that we could not change according to the standard. We said, well, what if, right? What if the standard would allow us to change this parameter? Would it really improve the performance or not? Well, in most cases, the answer was yes, it could. And the second approach was to develop an analytical model. It's a very nice one, frankly speaking. We didn't manage to publish it yet, so it's the second review round, but we are optimistic. And it provides very good results, as I'll show you in a minute. So here you find the papers that are referred here in the slide, if you're gonna have a deeper look into it. This is just a screenshot of the analytical model. I don't have time to explain it, so, but it's cool, believe me. If you like these kind of things, the model is pretty cool. But the coolest part is that you can see it here. These are just some examples of the type of results that you can get from the simulator and from the model. So the model provides the continuous lines. The simulator just provides the marks here. And you can see that the matching is very good. So the model works pretty well. So why using the model if the simulator is already pretty good? Well, the model takes something like a few hundred of milliseconds to provide the results. The model takes a few days. The simulator takes a few days. So the model is very convenient in this case. And playing with the model, we could find the optimal parameter settings in different scenarios. And what you realize is that if you compare the performance that you get using the standard configuration with what you can get by an optimal setting of the parameters, you can see that there is basically no comparison. You can really improve the performance if you set the parameters in the proper manner. So having a mathematical model or even a synthetic one that allows you to test the different configurations and find the optimal one for your specific case might be a game changer, might make the difference between an application that works and an application that doesn't work. We did the same thing in an industrial setting using some measurements for the industrial channel taken from the literature. We placed these measurements into the simulator. So we simulated the industrial channel, and we again tried different configurations and found the configuration that provided the best results in different scenarios. Here, the results are kind of disappointing. So LoRa is not really good for industrial scenarios according to our analysis, but it depends on the requirements, right? So if the setting generates just a few packets per second, then the probability of success is very high and the delay is reasonably low, around a few seconds here. If you increase the traffic, the load on the channel, however, the performance rapidly decreases. And you can't do much about that. Even if you increase the number of gateways, you improve you change the setting of your parameters, the performance are still limited. So again, in this case, the result was not positive, but was still interesting, right? So because it provides an answer to your question. All right. Then very quickly, we also use LoRa in a completely different context. So in a scenario where for which LoRa was not proposed, so LoRa was intended to collect data from static sensor, we try to use it on a dynamic scenario where we have drones moving over an area, and we needed to control the drones via remote stations, and we used LoRa to exchange the control commands to the drone and check whether this approach could work or not. Well, long story short, we actually did a lot of work here because we proposed a new model to describe the motion of the drones. We developed a Kalman filter that could use that model to predict the position of the drones. And then we designed the communication protocol in such a way that you use the transmission only if needed. So if the actual position of the drone was actually very different from the expected position. So we performed a very, let's say, optimized setting of the system. Let me skip results. But once again, using our simulator, we could evaluate the impact of some of the parameter settings of our system. And we could see, for example, that enabling automatic data rate selection, that is one of the properties of LoRa, at the network server, we could improve performance while enabling this automatic date rate both at the end node and at the network server. That seems to be clever, right? Seems to be better than just having one node that optimize the rate. Well, what we found is that if you let also the end devices optimize their data rate, actually the performance becomes worse. So sort of counterintuitive results. Why? Well, because there are a number of factors that come into play that are not easy to be predicted without a clever and careful analysis of your system. All right, so what is the conclusion from this very quick overview of this type of work? Conclusion is you need modeling. You need to know how the application works and what it requires in terms of communication capabilities. If you know this, if you can model this, if you can simulate this, then you can optimize your system even without changing actually the system, even without proposing something new, just playing with what is there for you, just to tune some knobs in the proper manner. Okay, so I skip this and I give the floor to my colleague Federico for the second part of the presentation that were supposed to be the more detailed one, but probably we will skip also that one.
Hi. So I will try to go very fast because we don't have time. So my name is Federico and I'm a PhD student of the SIGNET group, and my supervisor, of course, is Andrea Zanella. And today I will talk about my research work about network slicing, and in particular, how to exploit reinforcement learning to optimize a network slicing system. The motivation behind this research is that everybody knows that in the last years, telecommunication network get more heterogeneous, complex, and start to support very different service with very specific requirements. Just think about your mobile phone that can be used to watch movies, as we said previously, but also think about more specific user classes like public safety operators that might need to use the telecommunication system, the telecommunication network, for instance, to use a drone to monitor an area or doing something more specific. And to support all these different user classes using the same architecture, the scientific community in the last year proposed a new paradigm that is called network slicing. That means that implies that over the same architecture, over the same physical architecture, we can define multiple logical networks so that each of the network can be used to support a specific user class or a specific class of services, which is something very good because the services in the different logical network in the different slices are isolated, and you can better optimize the system resources, both the virtual one and the physical one, and you have a better adaptability. Okay, the problem in this context is that the system is very complex. You have multiple user classes, multiple many resources to be optimized. And in this system, it is very useful, especially when we consider scenario with very different user classes, like a public safety scenario, where you have, okay, emergency operator, like the fireman, like the healthcare professional that have to react to some critical event. And okay, and you say, okay, I have to support this new user classes, and I could, for instance, initialize a new network slice over the system to support them. Like in the picture before, you have part of the network resources dedicated to public safety operators. But the problem is, in a public safety scenario, you have critical events like an earthquake or a fire that can damage part of the network infrastructure, and therefore part of the resources can be not available to support your user classes. And so the system gets more complex, and in particular, it is very difficult to manage the system in a centralized approach. For that reason, in our research, we try to design a distributed approach that can optimize the network resources in a network slicing scenario. And to do so, we consider the deep reinforcement learning paradigm, which is a very powerful tool that combines reinforcement learning and neural networks to find complex solutions to manage a certain system and optimize a certain systems. And to do so, we consider a very general network slicing model where we have multiple flows contending for the same virtual and physical resources. And more specifically, each of the flow is characterized by specific requirements and a specific performance function that depends on the slice which the flow belongs to. So for instance, we can have a service for healthcare operators with very strict delay requirements, because healthcare operators have to communicate very fast with the end users, while if you have a service for video streaming, you have high throughput, and so you need a high capacity. But maybe you can increase your delay without degrading the quality of experience. And then we consider a general network slicing model where two main elements that are the links that provide bandwidth, of course, and then the nodes that are assumed to be connected with some mobile edge computing or network server and can provide the computational power to build the virtual network function of the systems. So, okay, and in particular in our research, in our paper, in our work, we consider two slices, one for normal user, that is the MBB slice, and one for critical user, public safety operators, we can assume, which is the URLC slice. And the goal of the system, of the work, is to maximize the system utility, which is defined as the average performance of each of the flow in the systems. To do so, as I said previously, we consider deep reinforcement learning. Reinforcement learning, for those of you that does not know anything about that, is one of the main paradigm that are within the machine learning field, and it consists in an agent that has to play with an environment and has to choose an action at each time slot, has to choose a new action and get a reward according to his action. And so the agent, the goal is to find the best combination between state and action to maximize the reward over a long term, over a long time horizon. In our case, we consider that we have an agent in each network location, and the agent will see the status of the network location, of the specific network location, like a link or a node, and it will do an action, which means that it will allocate the bandwidth of the link or the computational power of the node among the different flows that cross the network elements. And finally, it gets a reward that, of course, is proportional to the performance of all the flows crossing the links or the node, depending on what we are considering. Okay, more in particular, in this case, we consider a multi-agent system where we have multiple agents, not only one agent per element, but also one agent per flow, so that the system can be adaptable and can adapt to different number of traffic flows that cross the elements. Because of course, if you consider a scenario where 2 flows or 10 flows, the action space will change, because in the first scenario, I have to allocate resources among only 2 flows. But if we consider a scenario with 10 flows, I have more users, so I have to allocate resource in a different way. I will try to go very fast because I see people at the door. Okay, this is the picture of the scenario. So we have the agent that are located in the different network elements. And in particular, the deployment of the agent is distributed, but the training is centralized. So all the training is done by a central entity that is placed in a network server, for instance, and then the agents are deployed in the different network elements. Okay, we design some benchmark strategy to evaluate this system, and then we perform 2 training in 2 different scenarios that we call dumbbell network and triangle network that are simulative scenario. And then we implement the different strategies in the 2 scenario where we perform the training, and also in a 3rd scenario. And the interesting part here is that our solution, even if it was trained in specific network topology, after we implemented it in a different network topology, so in a different scenario, it works very well also in the new scenario. So the system was adaptable to different working conditions without the need of additional training. This is our box plot that represents the distribution of the performance, and the white line in the middle is the median of the performance. So the orange and the red one are the reinforcement learning based strategy, while the green one and the blue one are the benchmark strategies, and you can observe that in all the cases our solution is better. And and then we ask ourselves how we can further improve the system. And the answer was, okay, we could use transfer learning, so we can train the different learning agent to be adapted to work in a specific network location. And to do so, we consider to have, so we do not have, as before, a single agent or few agents that are deployed in all the network elements, but we have a specific agent per network element, and this improves the system performance. But at the same time, is less flexible, because you cannot anymore deploy the same agent in any network location. It has to work in a specific network location, because during the training, it was trained to operate only in that point. So we reduce the flexibility to improve the performance. Okay, and we get we can observe that the performance improves, as I said before. Then we do some other tests, but I will skip it. One last thing that I want to say is that an interesting part of this work, I have to. Okay. I will finish it. So I will skip to the conclusion. Okay.